All righty, back at it. Section 7.2 is all about properties of exponential functions. So kind of doing the same transformations, shifting up and down, side to side that we've done in previous units and chapters. So our EQ is how can I graph transformations of exponential functions. And just to kind of get us rolling, as a quick warm up, what happened or what transformation occurred to the parent function of the parabola as y equals x squared to get each one of these. So if I see a +2 inside the parentheses, I know that's horizontal, so it's right or left. Remember, this is kind of the opposite of what you would think. So this is a translation left 2. I see that -7 not in parentheses. That's a down 7. 3 in front of the x squared. Anytime I'm multiplying, that's a vertical stretch or a compression. Because I'm multiplying by something greater than 1. Kind of like yesterday, or in 7.1, we talked about exponential growth and decay. Since this number is bigger than 1, this is a stretch. X minus 5 squared. Again, that's opposite of what you'd think when as far as like right and left. So if you see minus 5, that moves to the right 5 units. And -1/3 x squared, there's actually 2 transformations going on. That is a vertical compression because of the 1/3. Factor 1/3. And then the negative is also flipping that parabola over the x-axis. So that is a x-axis reflection as well as a vertical compression. So we're going to kind of get into this a little bit today. It was usually pretty easy to tell between all of these 5 things when we talked about parabolas. One thing that can be tricky when we're talking about exponential functions. So you can see that both red and blue are exponential growth, and specifically positive growth. But the question is, if I go from red to blue, is that a vertical compression? Like, am I taking these points and shifting them all down to get the blue one? Right, which is one possibility. Or is it a horizontal translation? Meaning, am I just taking this entire graph and moving it to the right? So visually, it's tough to tell which one's which, and that's why we have to go to the equation. If you don't know what the equation is of those two, we can't tell the difference. You could actually make an argument for either one. So we're going to rely on the equation or the y equals to tell us what is going on with an exponential function. So when we talk about vertical stretches or compressions, okay, what's kind of interesting here is the parent function. If I asked you what's the parent function of this y equals 3 times 2 to the x, most of the time we're used to the parent function just being void of numbers and just being like y equals x squared, y equals square root x, y equals x to the third. In this case, the parent function has to, since the exponent is x, it has to include the number 2 as well. So the parent function is actually y equals 2 to the x. I could plug that into a calculator and I would get 0.25, 0.5, 1, 2, and 4. Okay. But then obviously that 3, which we talked about, is also the start value, is going to take all of those y coordinates and basically triple them. And so you could just plug into a calculator 3 times 2 to the x, and it will give you the numbers. But I could also just take each of these values and multiply it by 3, multiply it by 3, and multiply it by 3. Okay. So just understanding that the start value is also a vertical stretch or compression, while also like being referred to as the start value. So here, if I had y equals, so moral of that story, if I wanted to graph y equals 3 times 2 to the x, well, if I wanted to graph this thing, here would be my x coordinates, and here would be my y coordinates that I would graph. It's just how we get it from the parent function. Here, my parent function of just 1.5 to the power of x. So again, I can type these things into my calculator. I don't know. Oh, wait. Sorry. These are wrong. These should be here. Because we know anything to the 0 power is 1. And then this is 0.6 repeating. And this is 0.4 repeating. Yeah. Okay. So again, now if I wanted to graph y equals negative 0.5, again, two things going on here. There's a vertical compression of 1/2. So I'm basically shoving everything to its half of its original height. And then I'm also flipping across the x-axis reflection. Okay. So that would give me, instead of 0.4 repeating, this would be 0.2 repeating, negative. Instead of 0.6 repeating, this would be negative 0.3 repeating, negative 0.5, negative 0.75, and negative 1.125. Okay. Like it's good to talk about if it's a stretch or compression or what transformation is going on. But again, if this were me, I would just take that. I would just take the y equals equation, which was negative 0.5 times 1.5. Again, sometimes you can use the parentheses instead of the multiplication button. If I then hit second graph, I'll see all those values that we had right away. So it's just another way to do it. But understanding that the key here is understanding that the parent function is this entire thing, right? This whole thing is the parent function, not just y equals x. Okay, so vertical stretches and compressions. Vertical or horizontal translations, same sort of rules apply, right? If I have a parent function of 3 to the x, this is going to be that's 1, 3, 9. This is 0.3 repeating and 0.1 repeating. Then if I were to see this minus 5 out here, okay, again, anytime you see a plus or minus at the very end of a function, that should tell you that you're dealing with some sort of vertical translation, moving up or down. So this is actually going to move down 5, down 5. So I would have, if I subtract 5 from each of these, those decimals end up being annoying. Negative 4.8 repeating. Negative 4. Oh my lord. 6? Yeah. Negative 4, negative 2, and 4. Okay. Again, I just took all the y values and subtracted 5 from each of them. Okay. The key difference, or the new one, is you should see, in order to see a horizontal translation side to side, you will see a number being added or subtracted in parentheses in the exponent. Okay, so you'll actually see the power be x plus 2 or x minus 5, and that tells me that something is shifting either left or right. In this case, I'm moving everything to the left 2. So if I take my parent function, which is just 3 to the x, right, same parent function as before, so I take those same starting points of 0.1, 0.3, 1, 3, and 9. Okay. I know if I move left 2, this is the only time that I'm changing the x coordinate. So I'm going to take away 2 from all of these values and give me my new x coordinates of negative 4, negative 3, negative 2, negative 1, and 0. And then I'm just going to keep the same y coordinates. So because this function didn't change the y coordinates at all, I keep them the same. And then we just subtract 2 from those x values. Okay. So horizontal vertical translations. very similar. The only difference, again, being if you see the x plus 2, you need to see it in parentheses and very obviously in a power for that. So we're going to kind of put this all together and graph. This should say y equals. I don't know why it doesn't. So we're going to graph the equation y equals negative 2 times 1/3 to the x minus 3 plus 4. So what I'm going to do is I'm going to make a table for the parent function. And that's actually a lie. I'm not going to make a table for the parent function. I'm going to make a table for the parent function, but include the negative 2. So 1/3 to the x would be the parent function. Negative 2 is my start value. Because my growth factor is, or because it's a decay factor of 1/3, I know that my graph should end up going towards, should end up flattening out as I move from left to right. So what I'm going to do is I'm going to make a table of values for this in the calculator. So I'm going to go from negative 2 to positive 2, negative 2, negative 1, 0, 1, and 2. I'm going to go ahead and type that in, negative 2 times 1/3 to the x power, negative 2 times 1/3 to the x. Okay, I'm going to go to graph, or I'm going to go to the table, sorry. So here are my coordinates I'm going to use. So negative 18, negative 6, negative 2. So negative 18, let's see, where are we here? Negative 18, negative 6, negative 2, negative 0.6 repeating, negative 0.2 repeating. Okay, and you can see that those y coordinates are getting smaller and smaller, and they are approaching 0. So what I want to keep in mind is that right now the horizontal asymptote, which is something that we talked about in 7.1, that line that the graph is going to approach but not hit, right now it's at y equals 0. Okay. So what we're going to do now, right, to get the actual graph that I want, is I know this x plus 3 is going to move to the right 3 units. And I know that plus 4 is going to move up 4. Okay. So right 3 means I'm adding 3 to the x coordinates. So again, I'm just going to take, the x coordinates. I'm going to add 3 to all of them. So negative 2 becomes 1. Then I'm just counting up 1, 2, 3, 4, 5. Okay. If I move up 4, so 2 things happen here. By moving up 4, I know I'm just moving all of the y coordinates up 4. So I'm just going to add 4 to all the y coordinates. 1/3, yeah. So I'm going to add 4 to all the y coordinates. So we have, instead of negative 18, negative 14, negative 6 becomes negative 2, negative 2 becomes positive 2. That's 3.3 repeating, and this is 3.7 repeating. Okay. So as you can see, we're getting super. Now if you look at the y coordinates, 3.3 repeating and 3.7 repeating are approaching 4. So what happens here is not only do the y coordinates increase by 4, so I'm adding 4 to the y's, that horizontal asymptote, that line that the graph is approaching, is going to actually also move up 4 units. So now that horizontal asymptote is going to be at y equals 4. Okay. So I want to kind of show you what this looks like real quick. I'm going to use DESMOS for this instead. So if I go to DESMOS and I type in the original function, which was negative 2 times 1/3. Okay, do this quick. Negative 2 times 1/3 to the x power. Whoops. X. Okay. So you see the exponential decay here. I'm going up and flattening out towards 0, 0. There's my y-intercept of 0, 2. I can zoom in here, and again, feel free to do this on your own time. You can zoom in, and there's always going to be separation between the x-axis and that graph, which is why we call it an asymptote. If I do the same thing, but instead of that, I put the exponent of x minus 3. Oops, doesn't want to do that. Minus 3. X minus 3. I see that now I get that that horizontal translation. But then when I put the plus 4 out here, that's where the interesting thing happens. Okay. You can see how it's the same sort of shape, but now it's flattening out to 4 instead of flattening out to 0. So it's approaching 4, but never quite reaching it. So if you have a vertical translation up or down, you have to move the asymptote with it. Otherwise, like the asymptote will always be y equals 0. But for this, you do have to include that as part of it. So if I graph this now, obviously 1, negative 14 doesn't work. And we just saw what the graph looks like. 2, negative 2, 2, negative 2, 3, comma, positive 2, 4, comma, 3.3, and 5, comma, 3.7. That's not great. Positive 1 would be down here somewhere. Okay, but again, like, oh boy, just did exactly what I said not to do. I'm going to move that point down. Okay. Good. And you should be approaching it. And this is where, to show that there is indeed an asymptote there, we're going to put a dashed line on the graph. Okay, so I'm going to go straight across at 4 and put a dashed line. And what that does is that shows that our graph should be approaching that line, but not actually reaching that line. Okay. Oh, Lord. So, horizontal asymptote moves with vertical translations. Okay. And just show it on the graph by putting a dashed line like that. That way we know where we're talking. And we have an idea of where the graph's going. So just, that's really all there is to it. Again, the biggest thing is that that your horizontal asymptote moves with the vertical translations, not with vertical stretch, which is kind of interesting. Stretching something like multiplying, if you think about if the asymptote's at 0 and I triple it, it's still at 0. But if I add or subtract, that asymptote's going to move. So here's kind of a summary, right? Stretch, if the A value is greater than 1, it's a compression if A is between 0 and 1, and it's a reflection if it's negative. So these are all the same transformations that we've been talking about, but just kind of how it looks. So yeah, I don't know. That's in a nutshell. I'm not going to drag this out any longer. 7 to 21 odds. See you later.